Let's begin. So yeah, we're having free classes, and yeah, you guys are welcome to tag along. So we're going to look at forces, and all I want to show you guys is how we approach these questions on forces. Most of these questions are actually very complex, and it's rare that they would ask you guys these questions in an exam. But regardless, mine is to teach you guys how to answer these questions, regardless of whether they can ask them or not. And then understanding how these are approached perhaps will be very helpful in helping you guys to just understand physics altogether. Picture question 1, where we have a woman who stands on a scale. Let's go red. So this woman stands on a spring scale inside an elevator. So the scales, they read the forces with which it pushes upwards on the woman. See, this statement is very, very important. It tells you exactly how you answer this question. So to answer this question, I will be using this statement. That is where our answer will lie. The question is telling us to say that the scale reads the force with which it pushes upwards onto the woman. The whole question, of course, is longer than that. But because to answer this question, it depends on that single statement, I just want to make sure that you guys understand the interpretation of that statement. The scale reads the force with which it pushes upwards onto the woman. Imagine if this was the scale. Let's picture this to be the scale. And then this is the woman here on our scale, or any object that is literally just on this scale. What happens is that obviously you expect the weight of this object to bear down onto the scale, the weight to be pushing downwards. And let's take the weight to be mg. So the weight of this object will be pushing down onto the scale, and that weight, we're taking it as mg. So this is the scale here. But what else will happen? Well, wherever there's a surface, what I always emphasize is, provided there's a surface, an object is on a surface, then what we expect is going to be a reaction from that surface onto the object. So we expect that the surface will be pushing the object upwards. The force from the surface will be normal to the surface, and it will be acting from the surface to the object. And this is the reaction force predicted in Newton's third law. So that is going to be what comes out as our normal force. Now, the reading on this scale, according to this statement here, the reading on the scale is the force with which it pushes onto the woman. So in our case here, the reading the scale shows is actually the normal force. This is the force with which the scale pushes onto this object. So this is the reason why, if you have a scale just in your room, as in just in a normal environment where the room is not moving and so on, you quickly notice that if you used Newton's second law, sum of forces equals to ma, in the vertical axis, the object is not going up, the object is not going down. Again, this is in a normal setup where you adjust in your room and then maybe you're standing on your scale. It means that your acceleration is 0. If your acceleration is 0, then you have the normal going up, the weight going down, and then you have this is equals to 0, such that we conclude that the normal force becomes equals to mg. And again, I keep coming back to this statement. The scale reads the force with which it pushes onto the woman. So if you are standing on a scale and the scale is just in your room, it means that the force it is pushing on you, which is the normal force, would just be equals to mg, which is your weight. This is how a scale is used to determine the weight of an object. What it actually measures is the force it pushes onto the object with. But in a case where the scale is not moving altogether, it just so happens that the force it pushes this object with is actually equal to the weight of the object. So this is how a scale works. Now, if you understand that statement, then we can move on to actually answer the rest of these questions. Let's see, we have a comment. The screen is off. I think the screen is on because I have two devices I'm able to see on both sides, so the screen has to be on. Okay, so yeah, on the second device, I keep seeing it dimming out and so on. I don't know why. I hope it's not dimming for you guys too, but it's just for split seconds. So hopefully that's not disturbing you too much. Okay, so this is the key thing that you had to understand. What the scale shows is actually the normal force. If you understand that, then we can go on to hunt what that normal force will be in each scenario that will be described going forward. So I will copy this just in case you need it, and I will have it way at the end of this document. So will they allow me to go down? Yes, they will. So this is TS3, tutorial sheet number 3. And we're starting with question 1. Okay, let's get the question. So what are they saying here? A woman, and then they give us the mass of this woman. So the mass of this woman is M is equals to 45 kgs. So that is the mass of this woman. The mass of this woman is given to us as 45 kgs. Then there is this statement, which is very, very important. I think I spent some time describing how we use this statement. So the next thing that we want to see is, what are they now saying? What does the scale read when the elevator is accelerating? And there are given conditions here: accelerating upwards, here accelerating downwards, and just those two conditions. So if the elevator is accelerating upwards, it means that acceleration is positive, and the acceleration is 3.65 meters per second squared. And then if the elevator is accelerating downwards, then the acceleration is minus, because it's going downwards, so minus 3.65 meters per second squared. So this is the acceleration when the elevator is going up and when it is going downwards. So we have the answers to check whether we are doing the right thing. So these are the expected answers here. The screen is off. No, the other device is showing me that the screen is here this time. So when you, I think maybe the screen dims when your network is slow. So maybe when my network is lagging here, then it dims. But provided your network is okay, it should be fine. How is it? How is the screen? Because I have two devices connected, and if I'm able to see it on the second device, then the screen has to be okay.
So that if it was going up, so the acceleration would have been positive.
Yes, we actually have two values here. If you look at, let me highlight. Look at this one here. When the elevator is going upwards, that is 3.65. So for this case, it's the one I am taking this as positive 3.65. So this is for when it is going upwards. So I will use positive. And then the next one is when the elevator is going downwards. When the elevator is going downwards, I will take the acceleration as negative 3.65. Have you got that? Is that clear?
Yes.
Okay. So that is what we are working with. So let's get this information and let's start working out this question. What they're asking us to find is, what is the force? What is the reading on the elevator? Okay, so this is what we have. The first thing that we have to do is to picture what is happening to that elevator. So the woman is inside the elevator. The scale is also inside the elevator. So I am just looking at the scale which is inside. So let's picture this to be the surface of the scale. So if this is the surface of the scale, then the woman will be here. Consider the woman to just be an object that is right on top of this elevator, on this scale, not the elevator, the scale. The elevator can be pictured to be something outside like this, But we really don't want to focus on the elevator. We want to observe what is happening to the scale and the woman. So if you just picture the scale and the woman here, what we're saying is we will observe that the weight of the woman will be bearing downwards onto the scale. So the weight of the woman will be pushing down, and it will be equals to the mass of the woman times gravity. On the other hand, the elevator, not the elevator again, the scale, because we have the surface here, the surface of the scale will be pushing onto the woman, and the force from that will be going upwards, and that is actually the normal force. So this is what we are having here. Now, if these are the only two forces, again, I keep emphasizing, we are looking on the woman and the scale, not the elevator altogether. If we were looking at the elevator, we would have to also consider the force that is actually pulling the elevator upwards. But we're just focusing on the woman and the scale she is standing on. So if I just focus on this system for the woman and the scale and use Newton's second law in the vertical axis, observe that we will start with F is equals to ma. But in the first scenario where you adjust in your room, you are not going up, you're not going down. We said the acceleration was 0. This is the reason why the normal force was actually equal to your exact weight. But in these two cases, the question tells us to say that the elevator is accelerating up in the first case and accelerating down in the second case. So we will still be using this equation for both cases. But let's say when accelerating up, what do we see there? So when accelerating up, we observe that, like I mentioned earlier on, the acceleration becomes positive. Why? Because this object is going up. We're taking up as positive. Acceleration is a vector. So we then come back to Newton's second law, F is equals to ma. And now we want to account for all the forces that are present. If we go to the vertical axis, we count two forces, the normal and the weight. The normal goes up, so we take it as positive. The weight goes down, we take it as negative. This has to be what is equals to ma. So the normal is what we are looking for, remember? It's the reason why I took time to first emphasize that the scale reads what the normal is. So Fn is what we are looking for. The mass of this woman is given as 45. And then G is 9.8. This is what is equals to the mass again is 45. When the woman is accelerating upwards, the acceleration is positive 3.65. So this is what we are evaluating. Okay, so yeah, this is what we have. So we multiply 45 by 9.8. We get 441. And then we have 45 by 3.65. We get 164.25. So that from here, the normal force will be equals to 164.25 plus 441. This becomes equal to, when I add the 2, we end up with 605.25 newtons. So this becomes the reading on the scale. Now, this is if the elevator is going up. So this is the reading on the scale. Now, what if the elevator is going down? So when accelerating down. So when it is accelerating down, we recall that the acceleration will now be negative 3.65 meters per second squared. We're still starting with this expression, Newton's second law. The only difference is what the acceleration will be. So the normal will still point up, the weight will still be going down, and this will still be equals to ma. When substituting, we'll still have Fn minus the mass, which is 45, G, which is 9.8. The difference is now it will be 45 multiplying negative 3.65. This is the only difference. Notice that this is the only difference. I am now using negative instead of this positive, because here it was going up, so positive. Here it is going down, so negative. So we simplify. This will still be equals to that 441, and this will still be equal to that was what was that? That was 164.25. 164.25. The only difference is now this will be negative. So that now Fn will be equals to the 441 will now be positive. This will still be negative. And then you get the difference. So that is 441 minus 164.25. We get 276.75 newtons. So this is the reading on the scale when the elevator is going down, and this is the reading on the scale when the elevator is going up. Does it match the answers we were given? Let's see. 605, yes. 276, yes, it does. So this matches the answers which we were given. And I can actually even ask you guys one question. When do you feel the heaviest? Let's say you are in an elevator. When do you feel heavy? When the elevator is going up or when the elevator is going down? Try to imagine or think about the time you were in an elevator. You should agree with me that you feel heavy just when the elevator starts to accelerate up. You feel a little bit more heavy, but you feel lighter every time when the elevator starts to go down. This is actually showed in our values for the reading on the scale. We observed that based on the values, when the elevator was accelerating upwards, the reading on the scale was more. It was 605 newtons. And when the elevator was accelerating down, the reading on the scale was something smaller, 276, which agrees with the feeling that you have on an elevator to feel lighter when it is accelerating down and to feel a bit heavier when it is accelerating up. Okay, so I hope that was helpful, that extra bit of detail. But this concludes the first question. Do we have any questions before we go on to question 2?
Sir,
yes, please.
To use the same formula when dealing with elevators.
It depends with perhaps what you're looking at, but in this case, can you mute yourself just a bit?
Huh?
Mute yourself, then you unmute when you want to say something. There's a little feedback. Okay, that's better. So it honestly depends with the question. Physics can be unforgiving sometimes. But in this case, whenever you have a question, I always emphasize that start with a free body diagram. I always start by sketching the problem, picture what they're asking me. And in this case, this was the scale, and they were looking for a force. So the force was this one. So I first had to know exactly what the force was. And since it was a force I was looking for, I decided to also factor in the other forces which were present. And in this case, there were only two. The only other method that you can use perhaps here is in terms of work energy, but that would be even more complicated. Here, the sum of forces is the best approach that you can take. I don't want to say it's always to use this formula, but it's the best formula or the best way forward in this case. You get that? Have I answered that question? Okay, so Yeah, let's hope we've answered this question. I just avoided best because I avoided, is it always? Because always is too general. Great, we've answered that. Always is too general. Change the question just here and there. Add maybe, instead of giving acceleration, maybe just a change in position. Say this velocity is constant and so on. Then you can't work it out using forces, and you can, but the easier way becomes work energy. So yeah, in this case, this is the best approach. Let's move on to question 2. Let's do at least 2 questions. When a force of 450 Newton pushes a 20 kg box, as shown, the acceleration of the box up the inclined plane is given as this. So we have the force F, 450 Newtons. We have the acceleration, 0.7. We have the mass of this object, 20 kgs. What are they saying? Find the coefficient. We're looking for the coefficient here, the coefficient of friction. And the answer that they're asking us to match is 0.363. Will we be able to get this this answer or not? Let's get a picture of the question. We have a diagram to relate to. In our diagram, they're giving us this. They're giving us this. They are putting 45 here. Okay, so just a minute. Okay, so this is what we've been given, and that is what we are looking for. We have a picture of the question here. I just want to complete this. We have the object here. So you have that object there, and then the force is given there, and this is 450 Newtons. Okay, so let's quickly get this information, and let's see if we can pull it off. We're looking for the coefficient of friction. Okay, so let's go to a blank page. That is question 2. Okay, so let's see what is happening here. Well, there's really nothing very complicated here. Inclined planes are just intimidating. The first thing that you have to do is create a free body diagram. It's what I keep doing every time. So I just want to focus on this. So I'll just get this, and I want to bring it here so that we just analyze. We're dealing with forces here, and by looking at this, it's an inclined plane, there's a force given, and they're asking us to find the coefficient. Perhaps let me tell you why I want to take that approach. I want to find the coefficient. So let me start by looking at what the coefficient of friction is. The coefficient of friction, by definition, is the ratio of the frictional force to the normal force. So this is what the coefficient of friction is. In other words, if I wanted to find the coefficient of friction, then I must know what the frictional force is, and I must know what the normal force is. So I want to find these two forces if I am going to find the coefficient of friction. Now, that is where the job starts. Where will the normal force come from? So I am looking for two forces. I need to know all the forces present. So if I had, let's say, a plane like this one, we know to say an object here. In this case, we're being told to say that we have a horizontal force. This 450 is a horizontal force. I think it was specified in the question. So I will place that horizontal force. It doesn't matter really where you position it. So just want to show that this is a horizontal force. Then being horizontal, you have to see that it actually makes, you can use it to get an angle. If I was to draw a line like this one here, notice that this creates some form of a Z, as in this line here and this line here will be parallel to each other. A line that will connect these two, a straight line like that, it will ensure that this angle here will be the same as this angle here. And funny thing is that this angle, same angle which is the same here, it will be the same as the angle down here. So in this case, the angle that was given was the 45 here. But just by drawing a few lines, we have just indicated that if you could just draw something like this, the angle that you're going to have, not there, the angle that you're going to have something here and something here, The angle that you're going to have here will also be 45 degrees. Why do you need that 45? Because you want to find a way of breaking down this force F. You want to express it into a new X and a new Y. Remember what we always say? You want an X-axis that is parallel to the inclined plane. So you want forces to either go in that direction, and you want a Y-axis that's perpendicular to the inclined plane. So you want forces to either be parallel to the inclined plane or perpendicular to the inclined plane. So this will be our Y-axis. So this is what we want to work with, our Y and our X, and this is our Y. So we see that this force F is then at an angle. So we want to resolve the force F so that it now appears in pieces. Observe that the pieces will be, one will start from here. Look at where the head of the vector is. The head of the vector is this side. So we want to first go down. This will give us the Y component, and we want to move parallel to the X-axis. This will give us the X component. So you should be able to see this. It's here, I'm taking a little bit longer because I have to convince you guys. But when I'm doing this on my own, I am much, much faster. I would have been done with this question already. And since this angle here is theta, I know it will relate to this side here by sine, because opposite works with sine. So this is going to be the force vector F, then sine theta. And this one down here will be side by side with a theta. So it will be given by F, then cos theta. So that is one thing that you had to see there. And the other thing that you had to see is the weight. The weight of this object will be bearing straight vertically downwards. And also for the weight, you see that it is at an angle. For the weight, we have already looked at it for those who have been attending my classes. If the angle here is theta, then the angle here will also be theta. The X component of that weight will be a component that will be moving parallel to the X-axis. So it will have to be something like this. And the Y component will have to be something along this line. So it will be going downwards like that. So you see the X component will be opposite to that theta. So if this is the weight mg, it will be given by mg sine theta. And the Y component, the one this side, will be side by side with the theta. So it will be given by mg cos theta. A lot of lines on one diagram. I like my diagrams being smooth. So let me redraw that diagram with only the components and nothing else that I use to get my answers or to get my components. So if this is my object here, how I will draw my free body diagram if I wanted to solve this, those lines will confuse me. So I'll only show the components. The force F will have two components. The force F will have one component that will go down like this, pushing the object down. Remember, it's pressing downwards according to this arrow. So it is pushing the object down into the inclined plane. And this is the one that came out as F, according to this, F sine theta. So I'll write this as F sine theta. And it will have a component that will be pushing this force, this object up the inclined plane. So I'll put that one here, and this force will be pushing the object up the inclined plane. I can put it here, it's okay, or I can put it here. All I have to show is it's pushing the object up the inclined plane. So I can place it there, it's fine. So this is the force that comes out as F cos theta. We showed that here as well. The next thing is the weight. The weight had two pieces. One piece of the weight, we saw to say that it was bearing downwards in this direction as well. And that was given by mg cos theta. The other piece of the weight was this one, the one that was going down the inclined plane. Remember, all these forces are acting on the object. So there's no need for you to say this or to place it down there. It's acting on an object. So I might as well bring it here and say that this force will be going like this, and it will be given by mg. It's this one here. So it's this one. It was mg sine theta. So you have mg sine theta. The length of the arrows here do not indicate how big the force is. So don't really mind how long my arrows are. So now I have accounted for the weight and also for the applied force. There's only one thing that I'm left to do. Can you guess what I'm remaining with here? Friction. Nice. Friction. Friction is the one thing that I am now left with here. And in what direction will friction go? To know the direction of friction, you just need to picture in what direction is the motion. The question is saying that this object is being pushed to go up the inclined plane. So motion is up. If motion is up, then friction has to be back. So friction opposes motion. So friction will be among the forces which will be going backward. So I'll take this as force of friction. With this done, now we are ready to actually start summing the forces. I have accounted for all the forces present, and I have expressed them so that they are either vertical, meaning in that new y-axis, or horizontal, in that new x-axis. Let's start with the sum of forces in the y-axis, and say this is equals to ma in the y-axis. So again, it's up to you. You can start in the y, you can start in the x. I have started in the y here. It's easier to complete. There's one force that I've left here. There is one force. Wherever there is a surface, there will be a normal, a reaction from the surface. So what we expect here, the force that I left out was the reaction from the surface. And you know that reaction pushes perpendicular from the surface. So we expect that reaction to be in this direction, from the surface onto the object. And that is the normal force. That was the remaining force that I skipped out, but luckily I remembered before going very far. So in the y-axis, we now see three forces. A component of the force F going down, the reaction from the surface going up, and a piece of the weight going down. Let's take up to be positive. So we'll have the normal going down, a component of the force going down, that is F sine theta, and then also the weight going down, that is mg cos theta, equals to what? The object never sinks into the plane. It never goes up. It's moving up the inclined plane. So in the new y-axis that we are looking at, the acceleration there is 0. So because of that, it will be equals to 0. So in the end, we see that the normal force Fn will be equals to F sine theta plus mg cos theta. We know what F is, we know what theta is, we know what m is. So let's just get them and solve our problem. F is 450. M is 20. So we have 450 sine plus 20 times 9.8, and then cos. Let me get the angle now. The angle is, what's my angle? 45 degrees. So that is 45 sine 45 here and cos 45 here. So in the end, Fn comes out as, let's do some quick math. That is 450 sine 45, and then plus, we have 20 multiplying 9.8, and then cos 45. You guys can do this as well. Verify that what I'm writing here is correct. We get 456.79 newtons. This is what comes out as our normal force. The only thing left, if you look at the goal is to find the coefficient of friction. And from the y-axis, we have just found the normal force. We're now left with what force of friction is. So we now have to go and find what force of friction is. And where is force of friction? When I come to my diagram here, I see force of friction is in my x-axis. So I need to sum forces in my x-axis. So I count, don't forget, this red thing just shows the motion. It's not a force. So let me remove it so it doesn't confuse us. I count 3 forces in the x-axis, this one, and force of friction itself. So let's add the forces in the x-axis. I'll do it here. I'll take going up to be positive. So the only force going up is F cos theta. Then going down, we have mg, that piece of the weight, sine theta. Also going down, we have force of friction. This is what is equal to ma. In this case, we do have acceleration in the x-axis. Why? The question actually specified that this object is being pushed up the inclined plane, and this was the acceleration it was pushed with, 0.7. So we can use what we have been given. We'll first make A the subject. Okay, I need to just cut this. No, we'll just copy it. Okay, so this is our force. The acceleration is 0.7. We're looking for force of friction. So I'll take force of friction to the other side so that it becomes positive. I'll bring this to the left side, becomes negative. I have F cos theta minus mg sine theta. Then this becomes minus ma. Then this is equal to force of friction. So we can now substitute. I'll start with the right-hand side. F is 450. The angle is 45 minus the mass is 20. G is 9.8. Sine 45. Then minus the mass again 20. Then the acceleration 0.7, 0.7. So now we just simplify this. So that is 450 cos 45. We get 318 minus 20 by 9.8, then sine 45. Just up to that point, we get 179. Then we subtract 20 by 0.7, and we get 165. So force of friction here comes out as 165.60 newtons. Now we have the missing pieces. The coefficient we're looking for was force of friction over force normal. We now have both. Force of friction, 165.60. The normal force, we had this value. So we can now divide. So when we divide this, the answer by 456.79, we get the coefficient as 0.362. The coefficient has no units. Is this what we expected? We quickly go to the question and let's compare what we expected was question 2. And we expected 0.363. I wrote my answer as 0.362. I am happy with this. I think it is fine. So this is how you work out question 2. Okay, so I think we'll end here for tonight. More interesting questions coming up. 3, 4, 5, and 6 and 7 will be the most interesting ones. But we'll end here for tonight. Let's meet again tomorrow. So again, invite all your friends to join our free classes. All they have to do is download the app, join us in the WhatsApp group, and then let's learn together. All right, guys, have a good night. See you tomorrow night.